And let me zoom in, and you'll see that this is very complicated. The waves look very complicated, but they still kind of follow the same patterns. You have the same cycle. This could be like this shape kind of repeats itself over and over again. So let's see how this one sounds. Alright. It's kind of jarring. Alright, so that's the anatomy of a sine wave. So let's go back to the side. Sorry about that. Alright, so why is learning sine waves related to phonetics? There are two main reasons. Human speech and other human sounds are composed of complex sine waves. That's it. All the words, all the sounds that we make when we utter something can be analyzed and broken down as a series of complex sine waves. And as we saw, and because they are sine waves, all the sounds of speech have patterns to them. That is, the complex sounds are periodic. So all the sounds that we make as human beings, they have pattern. Their sound pattern. Their sounds are patterned, and therefore they can be measured and analyzed. Although I should make a note that there are some sounds that are aperiodic and random. So for example, fricative sounds such as the sh and the ch sounds do not display any periodic patterns, and the same thing applies for creaky voices like or breathy voices like how are you? But the general rule is that the sounds of human speech are periodic, and this periodic aspect of it has huge implications in terms of not only analyzing speech but also speech synthesis. So how we can create a program that that can mimic human speech, and also of speech recognition. So when was the last time that you talked over the phone and you were asked to say yes or no by some automated voice, and the voice on the other line actually recognized your answer, even though you were pretty sure that the voice on the other line was not a human being but a computer listening to your voice. So the sine wave characteristics of human voice has a lot of implications, both for practical and theoretical purposes. Alright, a little bit about harmonics. So human voices are composed of complex sine waves, and each individual sound wave of a complex sound wave that composes a sound is called a harmonic. The lowest sine wave of a complex sound wave is what is referred to as the fundamental frequency, or F0, and this fundamental frequency is that which we perceive as the pitch of a sound. So for example, if I say, "Are you hungry?" the rising pitch at the end of that "Are you hungry?" is purely a measurement of the fundamental frequency or pitch. Another way of understanding pitch is that it's basically the frequency of how fast your vocal cords are vibrating. Alright, so when we analyze language, all we need to look at is to look for the frequency and amplitude of each of the individual harmonics, or the individual components of the sine wave. That's it. We just look at the frequency and amplitude of all the different individual sine waves that compose a speech sound. So how do we visualize that? So here you have two ways of visualizing this this human sound broken into its individual sound waves. Um, the graph on top is what is referred to as a as an LPC spectrum, or a linear predictive spectrum, or a line spectrum. And basically it shows you, you basically tell the computer that's doing the analysis like how many peaks, frequency peaks, that it should look for. So these are the frequency peaks um, that the computer found for one sound. And the best way to interpret this graph is to look at it as a three-dimensional graph um, where time is sort of coming at your direction. So so you have the y-axis showing the amplitude, and the x-axis showing like the frequency, and you can imagine the z-axis, or the third dimensional axis, sort of coming right at you, and all the individual lines sort of kind of like ruler lines that are directed straight at your direction, and that would be the time dimension. The graph on the bottom is what is referred to as the DFT spectrum, and it shows you the energy level, or the amplitude of a sound at each individual frequency rate. And it shows that for each sound there are certain frequencies that show the greatest amount of energy, or the greatest amount of amplitude, and there are other frequencies where that are completely non-existent. Okay, so now that you know how we visualize a human sound, now what do we do with it? All right. So basically, if you imagine if you were able to cut up your head, like flip your head open, and just measure your glottis or your vocal cords vibrating, and measured the individual waves of that vibration, and this is what you would be seeing, this graph here. Like I said before, remember that the vibration of the glottis is kind of defined as the lowest frequency, the fundamental frequency, the lowest harmonic, so the lowest sounding sine wave of this complex sine wave. So the vibration of the glottis is kind of defined by its first formant, the F0, which is this one, and all the other frequencies sort of like fall down in a linear fashion. Alright, so what happens when the sound created by the glottis goes through the vocal tract? Imagine the voice, imagine kind of the sound as being, imagine your vocal tract as a tube with a lot of different configurations. An interesting, helpful way of think about the vocal tract is to think of it as a trumpet.